course Engineering Thermodynamics. In our previous lecture, we have started our discussion on the first law of thermodynamics for open system. And in terms of open systems, we have seen the mass conservation and energy conservation equation. Apart from that, I have also explained to you about a special type of process which is particularly known as steady flow process. And in case of steady flow process, our change of property of the control volume or system with time is equal to 0. So that's why we have come up with the equation that for steady flow situation, sum of all the inflow mass flow rates will be equal to sum of all the mass flow rates which are going out of the system. So under this condition, we will be having change in mass of the control volume with reference to time as equal to 0. If I talk about energy equation, so in terms of energy equation, we have seen for steady flow process, Q control volume, so energy transfer of the control volume minus net work transfer associated with the control volume. So in terms of net, I can write summation also over here. If I want to include, say, I have multiple interactions of heat and work. So this CV and over here, Q dot CV represents the net, like net input minus net output. Okay. So this plus we will be having summation of Mi dot into Hi plus Vi bar square by 2 plus G into Zi. That will be our energy inflow because of the mass minus summation of M dot E into He plus V bar E square, or I had written it V bar O square divided by 2. So let me write this also MOHO at outlet. Okay. Plus G into ZO. Okay. So this equal to 0. So this is nothing but my steady flow energy equation for steady flow process. Now this steady flow process is actually a very, very important process, and it is encountered in many of our engineering devices. So what we want to do basically, today we will try to see the application of this steady flow energy equation, particularly for some of our devices. Okay, so the very first device which I want to take over here is called as heat exchanger. Okay, so heat exchanger is nothing but a device in which the transfer of heat takes place between the different mediums. Okay, so let me draw a typical configuration of heat exchanger. So heat exchanger comprises of different volumes. So let me first take one pipe, and outside this pipe, let me consider that I have some arrangement, something like this. Okay, so now what will be happening? If you see over here, our configuration is such that we will be having certain flow of one medium. Say I have some hot medium, and that hot medium is actually flowing inside this pipe. Okay, so then I have another pipe outside, and that pipe is actually enclosing this entire internal pipe. And let me consider that I have some another cold medium, and that cold medium is actually flowing through this outside pipe. Okay, so that is flowing through this outside pipe. Now, what we will be doing, we will be considering that, let us consider M dot H is the mass flow rate of the hot medium. Now, if I take that we are having nothing but steady flow assumption valid. So if I take steady flow assumption, in that case, what will be happening? My mass flow rate of the hot fluid will be actually at the inlet will be equal to mass flow rate of hot fluid at the outlet. So that's why I am not representing any different symbol I and E over here. So what will be happening basically in both the sides, inlet and outlet, my mass flow rate of hot medium will be same. Okay, then so H I am using for enthalpy. So let me write complete hot over here for subscript. And similarly, what will be happening? Once again, our assumption of steady flow process is applicable. So in that situation, mass flow rate of cold medium I am writing as m dot c. At the inlet as well as outlet, it will be same, because we are saying that our assumption of steady flow process is valid, so we will not be having any accumulation. Now you can clearly see that this particular area over here, whatever now I am highlighting, this particular area is nothing but represents some surface, and on the both sides of this area we are having actually different fluids. So on the inner periphery of this tube wall, we are having nothing but hot medium, and on the outer periphery we are having nothing but our cold medium. Okay, so this area will be acting as some mode for the interaction of the heat between the two mediums. So you can clearly see that while these two mediums are interacting, we are not having any physical mixing between the two, because this tube is having some wall, and that wall will not allow physically these two different hot and cold streams to mix. Okay, but ultimately what is happening, this my hot stream is interacting through this cold stream in terms of energy interaction, and in particular we are already saying that we are having actually one as hot, one as cold. So it means we will be having some temperature gradient between the two. So because of that temperature gradient, what will be happening, we will be having transfer of heat from hot medium to the cold medium. Okay, so it means our heat will flow from hot to cold. Okay, so this point should be clear to all of you. So whatever the energy interaction we are having now in this particular case, that is nothing but our heat energy interaction. Okay, so now let me define. If I say that Hi is the enthalpy of this particular hot medium, so let me write H hot I as the enthalpy of this medium at inlet. Similarly, if I write H hot O as the enthalpy of this hot medium at exit. Okay, so what will be happening? Obviously, this hot medium will be actually losing certain amount of heat. So if it is losing certain amount of heat, it means H hot O will be less in comparison to H hot I. Okay, so enthalpy at inlet of the hot medium will be more because it is losing certain amount of heat, so its enthalpy will decrease. However, if we talk about cold medium, if I say HCI is enthalpy of the cold medium at the inlet, and if I say HCO is enthalpy of the hot medium at the outlet, in that case what will be happening? HCO will be more in comparison to HCI. Why HCO will be more? Because this medium is actually gaining certain amount of energy. So if it is gaining energy, obviously its enthalpy content will be actually increasing. Okay, now what I will be doing, I have to consider, now I have to define the boundary of the control volume. Okay, so let me consider that this is my boundary of the control volume. Okay, so let me define that whatever this dashed line I am drawing, this is nothing but represents the boundary of my control volume. So if this is my control volume, let me also consider, so generally in case of heat exchanger, we design the heat exchangers in such a fashion so that we are having only energy interaction between the hot and the cold medium, and there is no interaction with the surroundings. Okay, so that's why what will be happening at this particular point, if I see with reference to this medium, so Q control volume, Q dot control volume is actually 0. Why? Because we are saying that our boundary of the heat exchanger is nothing but insulated. So we are having insulated boundary of the heat exchanger. So because of that, what has happened, we are not having any energy interaction between our control volume and the surrounding. So Q dot CV in this particular case is equal to 0. At the same point of time, you can also see that our boundary of the control volume is actually not changing. And at the same point of time, we are not having any rotor or any other type of device where actually our work will be changing. So as any type of work interaction is there. So that's why for this particular control volume, our work interaction W dot CV is also equal to 0, because we are not having any arrangement which can produce work. Okay. So the only thing over here happening is nothing but the interaction of energy between the hot and cold medium. But that too, if I consider both these types as my individual control volume, in that case what will be happening, because our control volume is not having any interaction with the boundary, so whatever the energy interaction is happening, that is within the control volume. Across the boundary of the control volume, we don't have any interaction of energy. Okay, so now let me write down the steady flow energy equation for this particular system, whatever I have drawn over here. So if I write the steady flow energy equation, what will be happening? M dot into hot, it is coming with enthalpy H hot I. Okay, so if I say this is my inlet state, then similarly in terms of cold state, what we are having? M dot C is the mass flow rate of the cold medium, and it is coming with enthalpy HC I at the inlet. Okay. After that, we are having minus M dot hot. This is mass flow rate of hot medium at exit into H hot comma O. So exit state. Minus M dot C O into H CO. So that will be my enthalpy of cold medium at the outlet, and this will be nothing but equal to 0. Okay. So in this particular equation, because now we are not having any heat and any QCV and WCV for this particular control volume, so that's why what will be happening, I can simply write that my M dot hot into H hot I minus H hot O will be equal to M dot C into HCO minus HCI. Okay, so this is nothing but my energy equation when I have applied it on my heat exchanger. Okay, so in case of heat exchanger, what will be happening? Because we are considering our control volume boundary outside the heat interaction zone, so whatever the heat interaction is taking place, that is within the control volume. So that's why we can clearly see that whatever the amount of heat, so M dot hot into H hot I minus H hot O, it represents the change in enthalpy content of the hot medium, and HCO minus HCI represents the change in energy content of the cold medium. Okay, so whatever the change is happening in the energy content of hot medium, that will be nothing but equal to change in energy content of the cold medium, because we are not having any interaction of these mediums with the outside surroundings. Okay, one special case of heat exchanger I can take. So let me specify one special case of heat exchanger. So I may have a situation that I have the exact geometry of the heat exchanger as given in my previous slide. So once again, I am drawing it over here. But along with this, what I have, so over here I have some hot medium, and from here I have some cold medium. But now what I am doing, instead of considering the entire heat exchanger as my control volume, if I take only this internal pipe volume as my control volume, so in that case, what will be happening? So now if I take only this pipe volume as my control volume. Okay, so now what we are having, only the inner pipe volume I am taking as my control volume. So whatever is happening inside the cold medium, I am having no concern. So in this particular case, my control volume only includes hot stream. Okay, and what is happening outside in the cold stream, that is nothing but acting as my surroundings. So now cold stream is acting as surroundings. So now for this particular control volume, if you see what we will be having, obviously our heat will be transferring from the hot medium to the cold medium. Okay. So in this particular case, what will be happening? We will be having some flow of heat from hot to cold medium. So let me write that flow of heat as say Q dot Cv, because my control volume is now only the hot medium, and hot medium is losing certain amount of heat. So that's why we will be having some QCV interaction over here. Now if I apply the energy equation for my this new control volume, so in this case what will be happening? I have transfer of heat and it is going out of the control volume. So minus Q dot Cv, I don't have any work interaction. Apart from that, I have some mass flow rate m dot hot, which is entering at the inlet. So I'll be having m dot hot, and it is entering with enthalpy h hot I, and m dot hot once again is leaving out of the control volume, and it is leaving with enthalpy h hot O. Okay, equal to 0. So now in this case, you can clearly see that rate of heat transfer across the boundary of the control volume will be nothing but equal to m dot hot into h hot I minus h hot O. Okay, so that is something which we have got while we are considering only that our hot medium is actually control volume. So in the similar way, if you only consider your cold medium as the control volume, in that case you will be finding QCV equal to m dot C into HCO minus HCI, and ultimately we will be getting the balance situation as I have shown you earlier while we have taken entire thing as our control medium. Okay, so this particular device which facilitates the transfer of heat in between the two mediums, that we call as nothing but our heat exchanger. Now heat exchanger can be of multiple kinds. So one of the heat exchanger where only we will be having sensible heating of the medium. Okay, so we may have heat exchanger.
Excuse me, sir.
Yes.
So in the previous case, will QCV not be negative positive? So mine plus QCV.
No, QCV will not be positive because whatever the control volume you are taking, that is a hot medium, and heat is going out of the control volume. So heat out is taken as negative. Okay. If we are taking cold medium as control volume, for that obviously this heat is actually entering into the medium. So for cold medium it will be plus QCV. Okay.
So, but final answer is positive in that case. It should be negative.
No, final answer has to be positive because already we have included our sign convention. Already we have mentioned that our QCV is negative. So if we have already included sign convention, it automatically says that whatever the QCV is there, this is nothing but the heat going out of the system, because already we included the sign convention. So that's why we have to say that this heat is actually going out of the system. Okay.
Yes, sir.
Okay, so now what I am saying that we may have different situations. So for example, in one of the case, it may be there that our device, our fluid, whatever working fluid is actually flowing inside the pipe, that is actually not in saturated state. So if it is not in saturated state, we will be having either sensible heating or sensible cooling. Obviously, for hot medium, we will be having sensible cooling, and for cold medium we will be having sensible heating. Okay, so it is nothing but that the temperature of the hot medium will be decreasing and temperature of the cold medium will be increasing. Okay, apart from that, we may have another situation where our one of the medium is actually in the saturation state. Okay, so it may happen that if our hot medium, whatever I am considering, say this hot medium is actually entering at saturated vapor state. So if hot medium is entering at saturated vapor state, what will be happening? For hot medium now, we will be having the change of phase from vapor to liquid. Okay. And I am considering that for cold medium, I am having only single phase resign. So here I'll be having nothing but sensible heating. Okay. So it means in this type of particular heat exchanger, what will be happening? Whatever the latent heat loss will be there in our hot medium, same amount of sensible heat gain will be there in our cold medium. Okay. And over here, our hot medium will be changing from, it will change from saturation vapor state to the saturated liquid state. Okay. So this type of device is called as our condenser. Okay. So the device where our vapor changes, or a heat exchanger device where saturated vapor changes into liquid state, that particular device we call as nothing but our condenser. And condenser is having many engineering applications. So probably if you see your home refrigerator, on the back side of the home refrigerator, we are having one condenser. So how it works, we will try to see subsequently. Moreover, in our power plants also, we are having actually coal-based thermal power plants, we have condensers. Okay, so how these are applicable, we will try to see in our subsequent lectures. Apart from that, we will have...
Sir, if we assume that the entering liquid is entering state of the that is just above the saturated pressure, then will we consider both the energies like sensible heating and latent heat?
Yes, part will be sensible and part will be latent. Okay.
Okay.
Now let me consider that this is my hot medium, and inside hot medium only this is in the single phase resign. Here we are having only sensible cooling. So for hot medium we will be having nothing but our sensible cooling. And outside, if I consider that I have a medium which is entering at saturated liquid state, so obviously we will be having, depending upon the amount of heat transfer, we will be having some vapor at the outlet. Okay, so in this case our liquid is actually converting into vapor. So this type of device is known as nothing but our evaporator. Okay, so evaporator is also very important component of our refrigerator and air conditioner, etc. Okay, so that we will try to see later. Now let me take up another kind of device. So next type of device is something which is known as a turbine. Okay. So what is a turbine? I have already told you that turbine is nothing but a mechanical arrangement in which we allow the high pressure fluid medium to enter, and then in this particular turbine control volume, we have some rotor kind of arrangement, and that particular rotor arrangement actually facilitates the conversion of energy of liquid, our fluid medium, into the shaft work. Okay, so we are having rotors inside. Okay, and these rotors are mounted on a common shaft. Now at this particular point, while our working fluid will be entering, it will be having, say, mass flow rate m dot, and it will be having some high pressure pi, enthalpy hi, okay, and some velocity vi it will be having, vi bar. Then similarly at the outlet, when it will be going, the mass flow rate has to be same, because we are saying that our device is nothing but steady flow process device. So here pressure will be PO, enthalpy will be HO, and velocity is, say, VO bar. Okay, so now what will be happening in this particular turbine, we will be having actually rotation of this shaft, and we will be getting certain amount of work. This work we call as, say, W dot S as our rate at which shaft work is being done. So nothing but what will be happening, at the expense of the fluid pressure, we will be having actually some mechanical output work which will be obtained in terms of the rotation of the shaft. Okay, so now depending upon the medium of our working fluid, actually we are having different types of turbines. So if we are having steam as our working medium, high pressure steam as our working medium, in that case we refer this turbine as nothing but steam turbine. If we are having high pressure gases as our working medium, we call our turbines as nothing but gas turbines. Okay. So if we do the thermodynamic analysis of this particular turbine, so what I'll be doing, I'll be defining my control volume. So let me consider that this is my control volume. So basically what I am doing, whatever the surface or periphery of turbine is there, that only I am considering as my control volume. Okay. So from this control volume, you can see W dot S amount of work is actually done by this turbine. Okay. And m dot mass flow rate is entering and same amount of mass is actually going out of the turbine. Okay. Apart from that, if you try to see what will be happening, the flow inside the turbine, flow of medium inside the turbine will be so fast that whatever the fluid is traveling from inlet to outlet, that will not get sufficient time for the heat transfer to take place. Okay. So because of the fast process inside the turbine, what we consider that we are not having any heat interaction with the surrounding. So that's why Q dot Cv equal to 0, and we say that the process inside the turbine is nothing but adiabatic. Okay. So we are considering that process inside the turbine is adiabatic. Apart from that, the change in elevation at inlet and outlet is almost negligible. So because of that, we will be considering that our change of potential energy delta PE will be equal to 0. Okay, because change of elevation in case of turbine will be very, very small. Okay. Apart from that, obviously, while our stream will be entering, that will be having certain inflow velocity as well as it will be having certain outflow velocity also. Okay, so while we will be taking the change of outflow minus inflow velocity, that will also be small in comparison to the change of enthalpy. So that's why delta kinetic energy is also considered as 0 for the case of the turbine. Why? Because majority of the work whatever we are obtaining from the turbine, that is at the expense of its pressure. So it means it is only the main responsible region is pressure. So pressure at outlet will be very, very small in comparison to the pressure at inlet. So as pressure is already accounted in our enthalpy term, so that's why change of enthalpy will be significant. However, change of kinetic energy will be very, very small. Okay. So now if for this particular turbine, I apply my steady flow energy equation. So what will be happening for turbine, we are having Q dot Cv equal to 0 minus W dot Cv, because work is done by the system. So I'll be taking it with positive sign, plus m dot is the mass flow rate of the working medium and it is coming with enthalpy Hi. Okay, at the inlet, and all other energies, kinetic and potential energies, I am actually neglecting. Minus m dot is same amount of mass flow rate is actually also leaving from the turbine and it is leaving with enthalpy Ho. So that is equal to 0. So from this particular formulation, I will be getting that work done by this control volume WCV is nothing but equal to m dot times Hi minus Ho, where Hi is the enthalpy at inlet, Ho is enthalpy at outlet of the turbine. Okay, so this is the amount of work done which we will be getting from our turbine when it is operating under the steady flow process conditions. Okay, so this is the work done by the turbine. Now, please mute your
So we have not included shaft work.
That is WCV. Shaft work is only I am calling as WCV.
Sir, please explain why is kinetic energy is 0 here.
So it is better if I take all the doubts in the doubt clearing session. Okay, so now let me complete. Okay, our next type of device, which is just reverse of the turbine, is something which is called as pump or compressor. A device which is reverse of the turbine is actually called as either pump or compressor. Okay, so the term pump is specifically used when we are having liquid as our working medium, and the term compressor is used when we are having gas as our working medium. So when we are having gaseous working medium, then we call our device as nothing but compressor, and when we are having pump as our working medium, we call our device as nothing but pump. Okay, So pump is construction wise, it is nothing but just a reverse of the our turbine. So in case of turbine, we were having expansion of the fluid from inlet to outlet. So in case of compressor, we will be having nothing but compression of the medium from inlet to outlet. So this is my inlet I, and this is over here, say, outlet. Okay, and this is reverse of the turbine. So in case of turbine, what we were doing actually, we were employing the fluid pressure. So the change of fluid pressure was actually causing some mechanical work to happen. Now in this case, what we will be doing, in this case actually, we will be supplying some shaft work. So from here, some amount of work will be supplied to this shaft, and this shaft work will be doing certain amount of work on the fluid medium. And because of that, what will be happening, if Pi is my pressure at the inlet and Po is pressure at the outlet, Po pressure will be more in comparison to that of Pi pressure. Okay, so the basic idea is that in case of pump, what we do, we impart some kinetic energy to our medium, and then we are having some diffuser section within the casing of the pump or compressor only, and that diffuser system actually converts that kinetic energy into the pressure energy. Okay, so what is this diffuser? That also I'll now explain you in the subsequent slide. So overall idea is that we are supplying certain amount of mechanical work, and that mechanical work is actually increasing the pressure of the working medium. So earlier what was happening, the pressure was producing certain amount of mechanical work. Now over here actually the amount of work supplied will be producing will be increasing the pressure of the working medium. So if I consider that Hi is enthalpy at inlet and Ho is enthalpy at outlet, now what will be happening for that this pump or compressor, majority of the assumptions which we have considered for turbine all are actually valid. Okay, so let me now write down the equation considering all these assumptions valid. So if I write Q dot Cv, that will be equal to 0 minus, now I have to write WCV. Okay, so now this work is actually done on the system. If work is done on the system, I have to put negative sign with this work. So let me write W dot, say S I am writing as shaft work which is done on the system. So now as work is done on the system, so that's why I have to use over here negative sign. Okay, plus M dot is, say, the mass flow rate. Now mass flow rate at inlet and outlet will remain same, then only steady flow assumption will be valid. So M dot into Hi is the enthalpy at the inlet minus M dot into Ho is the enthalpy at the outlet, and this will be equal to 0. All other assumptions of potential energy, kinetic energy, etc. will be applicable as it is. Okay, so that's why what will be happening, if I now calculate the amount of work, so W dot S will be nothing but M dot times Ho minus Hi. This is actually the rate at which work is done on the pump in order to obtain the desired rise of pressure of the working medium. Okay, so now in case of pump, as I have told you that we have to consider actually Q control volume equal to 0. So while we go into the mechanical perspective, if we go into the physical construction of the pump, so we are having actually two types of arrangements. One we call as nothing but rotary pump or compressor, and another arrangement is actually referred to as reciprocating arrangement. Okay, so in case of rotary devices, we are having two types of further divisions. Either we are having actually axial flow compressors, or we have centrifugal. Either we have axial or we have centrifugal devices. So this is nothing but these devices are almost identical to that of the turbine construction. So in these devices actually we will be having certain rotor over here. So let me specify, say this is my rotor, and this rotor will be rotating at certain velocity. So while the rotor will be rotating at certain velocity, it will be actually imparting certain kinetic energy to the working medium. Okay, so once this kinetic energy is imparted to the working medium, after that we will be having over here some diffuser section. So we will be having some diffuser section, means a section of increasing cross section area. So in this increasing cross section area section, what will be happening? Whatever the kinetic energy is imparted to the working medium, that kinetic energy will convert it into pressure energy. Okay, so these type of devices are referred to as nothing but rotary pump or compressor devices. And for these devices, what will be happening? Our assumption of adiabatic boundary will be applicable. Okay, so for these particular devices, assumption of adiabatic boundary will be applicable. Another type of devices, we are having reciprocating devices. So in case of reciprocating devices, what will be happening? We will be having some cylinder, and in this cylinder we will be having some inlet valve, we will be having some outlet valve. Okay, and then over here we will be having some piston, and this piston will be actually connected to some through some assembly. This will be connected to some prime mover, which will be supplying the mechanical work, and our working medium will be actually compressed inside this piston cylinder arrangement. Okay, so in one stroke, while this piston will be moving in downward direction, we will be having inlet of the working medium, and while this piston will be moving in upward direction, during that time outlet valve will be open and we will be having the outflow at high pressure. Okay, so in this type of reciprocating devices, we have the generation of significant amount of heat. Okay, so in case of reciprocating devices, significant amount of heat generates. So because of that, we have to remove that amount of heat. Okay, so for removing that amount of heat, what we do, there are two types of arrangement. Either we put some additional fins over the surface of this cylinder. So these fins actually helps in dissipating the energy at faster rate, or otherwise what we do, inside this cylinder we provide some small channels, and through these channels we allow the flow of coolant. Okay, so there are two types of arrangement. Either we allow the flow of coolant through some small jackets inside our container, or we are having some additional arrangement which will be enhancing heat transfer. Okay, so whatever I have told you in this particular slide, this is not very much relevant to your content, but this you should know that we are having two types of devices, rotary and reciprocating. So in our thermodynamic analysis in this particular subject, majority of the times, if any condition is not specified about the heat transfer, we will be considering that our pump or compressor is not always adiabatic. Okay, so while you will be going through your further subjects of fluid machinery, etc., there you will be finding more details about these compressors. Okay, so at the moment you have to consider for this particular subject that if no condition is given about the heat transfer, you have to consider that process inside the compressor is nothing but adiabatic. Okay, now another very simple kind of device, something which is referred to as nozzle. Okay, so the meaning of nozzle is, or the idea of using the nozzle is, this particular type of device is used to increase the velocity at the expense of the pressure once again. Okay, so what we do in nozzle, in case of nozzle, we physically take the construction of our device in such a fashion so that if this I consider as my inlet section and this I consider as my outlet section, so if some medium is flowing at the inlet it will be having very large amount of area. Okay, and while it will be, the flow will be, or the medium will be moving through this particular nozzle, what will be happening, the cross-sectional area will keep on decreasing. Okay, so when cross-sectional area will be decreasing, ultimately what will be happening, our pressure energy will convert into the kinetic energy. Okay, so if I say that my VI bar is the velocity at the inlet of the nozzle, if working fluid is coming at say m dot mass flow rate, If I say my device or the process is steady flow process, in that case what will be happening? Mass flow rate will remain m dot only, and if V bar O is my velocity at the outlet, this V bar O will be very high in comparison to the velocity at the inlet. Okay, so because we have designed mechanically this arrangement in such a fashion so that our pressure energy is actually converting into kinetic energy. Okay, so because of that we will be finding significant increase in our velocity, okay, at the expense of pressure. For this nozzle also, let us consider that HI is enthalpy at the inlet and HO is enthalpy at the outlet. Now, if this is my control volume, so I have to define some control volume. So this is, say, my control volume. Once again, the process through the nozzle is very fast, very rapid. So because of that, we will not be having any heat interaction across the control volume boundary. Moreover, we are not having any additional arrangement to produce work. So that's why work interaction also in case of nozzle will be equal to 0. Okay, so the process inside the nozzle is adiabatic and we are not having any work interaction. Okay, so now if I apply the steady flow energy equation, what I will be finding that Q dot CV, which is 0, minus W dot CV, that is also 0, plus M dot into HI plus VI bar square by 2. Once again, change of potential energy is negligible for the nozzle because we are not having significant difference of elevation between inlet and outlet. Minus M dot into HE plus V bar O square. So I am writing it as HO plus V bar square divided by 2 equal to 0. Okay, so from this you can clearly see that M dot into HI plus VI bar square by 2 will be equal to M dot into HO plus VO bar square divided by 2. Okay, so now what will be happening? M dot will be cancelling because it is same. Okay, and one more assumption I can take. I have already told you that my VO bar is very large in comparison to VI bar. Okay, so in that case, what will be happening? VO bar square divided by 2 will be very large in comparison to VI bar square divided by 2. That's why what I can do, this VI bar square by 2, I can actually neglect. So if I am neglecting this, I will be having my HI will be equal to HO plus VO bar square divided by 2. And finally, I will be finding that VO bar will be equal to square root 2 into HI minus HO. Okay, so the change of enthalpy will be nothing but giving us the velocity at the exit of the nozzle. Okay, so nozzle is employed in many applications. So for example, we are having nozzles in our diesel engine as a diesel fuel injector, while we are having at the inlet of the nozzle, we are having and at the outlet, we are having high velocity in order to have good automation of the diesel fuel. Okay. Apart from that, in our rocket or gas turbine engines also, if we have to create the propulsion, so what we want very high velocity at the exit of the engine, gas turbine engine. So that's why we are having there also nozzle where we expand high pressure gases after the combustion chamber on the nozzle, and that creates extremely high velocities. Okay. Then next kind of device, which is just opposite to that of nozzle, is something which is called as a diffuser. Okay, so the task of the diffuser is nothing but reverse of nozzle. So in case of diffuser, what we do, we convert the kinetic energy into pressure energy. So over here we will be having the profile as nothing but reverse to that of nozzle. So inlet will be at low cross section and outlet will be at increased cross sectional area. Okay. After this one, we will be going to a very special device, and that particular special device is actually called as a throttling device or throttle. Either we call this as throttling device or we simply call this as nothing but throttle. Okay. So what is basically throttle? If I take a pipe and in this pipe, if I make a sudden contraction, okay, so if I have sudden reduction of the cross section, so what will be happening? If I say take any point at the inlet of this cross section and one point at the downstream of this sudden change of cross section, so we will be having this as say my inlet point for this throttle and this as my outlet point. So I will be having the mass flow rate as m dot. Obviously, whatever the mass flow rate is entering, in order to ensure the steady flow process, that mass flow rate has to be same. I can say HI is enthalpy at the inlet, PI is pressure, and over here HO is enthalpy at outlet and PO is pressure. Okay. So in this particular case, what will be happening? While we have already seen in case of nozzle, while we are having gradual reduction of the cross section, in case of gradual reduction of the cross section, actually pressure at the outlet decreases, and that decrease of pressure leads to increase in velocity at the outlet. Okay. However, if we are having sudden contraction of the cross section in our pipe, in that case, what will be happening? Obviously, we will be having significant drop in the pressure. So if we are having significant drop in the pressure, we are saying that expansion of the fluid is happening. We will be having expansion of fluid, means we will be having significant drop of pressure, but we will not be having increase of velocity. So if Vi was velocity at the inlet and Vo is velocity at the outlet, our Vo bar will be nearly equal to Vi bar. Okay. So what we are having over here, though we are having significant drop of the pressure, but that significant drop of the pressure has not caused much change in our velocity. Okay. So it means our velocity has not changed. So it means we will be having pressure is changing but velocity is not changing. Why velocity is not changing? Because in our system we have done sudden contractions. Okay, so because of the sudden contraction, though pressure has changed but velocity has not got sufficient cross-sectional change which has to be gradually there in order to increase it. Okay. So in this particular type of case, what will be happening? The process will also be fast. So because of the fast or rapid nature of the process, QCV equal to 0. Okay. So heat interaction will be equal to 0. At the same point of time, we are not having any arrangement for producing some work over here. So that's why W dot CV will also be equal to 0. Okay. So if these conditions are applicable, now if I apply the steady flow energy equation, I'll be finding that m dot into HI and as VO bar and VI bar are almost nearly equal. So that's why we will not be having actually any change of kinetic energy, and is also same. So change of kinetic energy and potential energy will be negligible. So I'll be having m dot into HI minus m dot into HO will be equal to 0. Okay. And finally, I can say that my HI is equal to HO. Now we know that HI is nothing but UI plus PI into VI, that will be equal to nothing but UO plus PO into VO. So it means that my PI is decreasing. So in order to ensure this constant enthalpy condition, so it means the process inside this throttling device is nothing but our isenthalpic process. The enthalpy of the process is constant. So the process over here is isenthalpic process, and in this particular isenthalpic process, we know that PO is very, very small in comparison to PI. So that's why our specific volume at the outlet has to increase in order to make our enthalpy same. Okay. So the more details about the throttling process, I will try to give in our next lecture. Now I'll stop at this point.